In this video, we're going to go ahead and talk a little bit about how to define radicals and some of their properties. We say a square root of a number is one of its two equal factors. Namely, 5 is a square root of 25 because 5 times 5 equals 25. And so we have two equal factors of 25. In a similar way, a cube root of a number is one of its three equal factors. That is, we could say negative 3 is the cube root of negative 27 because negative 3 times negative 3 times negative 3 is equal to negative 27. Now, with that said, we can go ahead and make a general definition of an nth root of a number. Throughout this, we're going to let a and b be real numbers and let n be a positive integer that's greater than or equal to 2. If a equals b to the n, then we say b is an nth root of a. If n equals 2, then the root is a square root. And if n equals 3, then the root is a cube root. So, for instance, what is a square root of 25? Well, as we saw before, we know 5 is because 5 times 5 equals 25. However, there's a little bit of a thing here, and this is why we said a square root, because we could also say negative 5, because negative 5 times negative 5 is equal to 25 as well. So notice that we said b is an nth root of a. That is, we could have multiple different roots. Well then, that leads to another definition. So again, let's let a be a real number that has at least one nth root. Then we say the principal nth root of a is the nth root that has the same sign as a. Further go on to say that it is denoted by a radical symbol. Which looks like this. Now, when n equals 2, we simply write the radical symbol of a, but without any index there, because it's understood to be 2. Yes, going back to what we talked about before, it is important to note that if we write the square root of 4, it is not equal to plus or minus 2. The square root of 4 also is not equal to negative 2. The square root of 4 is simply just 2. It is also important to note in this, again, some terminology in this notation. Namely, this is called the root or index. And this number a is called the radicand. What the bottom line of all of this is that if you take your own even root, you have to add plus or minus. That'll come into play when we start solving equations. In the meantime, the important thing to realize is that if the even root is given to you, it will already have the sign that it needs on it. So you don't need to add any signs, just take whatever sign is given to you. So now let's go ahead and work some examples. The square root of 36, well, since 36 is 6 times 6, we say, oh, well, this pulls out and tells us it's the equal factor, so just 6. Similarly, this would be negative 6, because the negative is applied after the square root. Important thing to note, exponents and radicals have the same order of operations. Here, we notice that 125 over 64 is the same thing as 5 over 4 times 5 over 4 times 5 over 4. Thus, since a cube root is one of the equal factors of the three equal factors, we have that this is 5/4. Here we can write negative 32 as the equal factors negative 2 times negative 2 times negative 2 times negative 2 times negative 2, which is simply negative 2 because we have 5 equal factors. Finally, with this example, one might expect that we could simply write, oh, well, negative 3 times negative 3 times negative 3 times negative 3. However, that is not negative 81. That is actually just 81, because a negative times a negative is a positive. This leads to a dilemma, and actually, here we actually have that this does not actually create a real number. This is weird because we haven't run into this yet in these notes, but we will find later on that there is a way to deal with these, and these create a new set of numbers called the complex numbers. So now it's your turn to go ahead and evaluate some of these expressions. So pause the video, and on the count of 3, I will reveal the answer. 1, 2, 3. So now you can go ahead and check your answers. Something useful to consider when calculating squared and cubed roots are what's called perfect squares and perfect cubes. So integers such as 1, 4, 9, 16, 25, 36, 49, etc. These are all called perfect squares. This is because they have integer square roots. Square root of 1 is 1, square root of 4 is 2, then 3, then 4, then 5, then 6, then 7. In a similar way, integers such as 1, 8, 27, 64, 125, I don't know off the top of my head what 6 cubed and 7 cubed are, so we'll just write ... ellipsis marks. These are called perfect cubes. Again, because they have integer cube roots. Now, that was something useful. Here's something a bit more troubling. If we do the square root of 6 squared, that's the square root of 6 times 6, which is in fact 6. However, the square root of negative 6 squared is negative 6 times negative 6. But if we do that multiplication first on the inside of the radical, in a sense it's saying that we apply the radical after we've done the multiplication on the inside, we have square root of 36. But the square root of 36 is just 6. This leads to an interesting dilemma, namely our conclusion out of this, and you can do similar examples with other numbers, there was nothing special about 6 in this case, is that the square root of a number squared is always its absolute value. So for our first property, we have that we can interchange the order in which we do the radical and the exponent. This is again because they have the same order of operations. So for example, if you want to evaluate the cube root of 8 squared, instead what you could do is you could do the cube root of 8 and then square your answer. That is, cube root of 8 is 2 because it's a perfect cube. 2 squared is 4. Here, much like exponents, a radical of a multiplication is the same thing as the radical of one number times the radical of the other number. In a similar way, the division also works as well. So for example, if I want to evaluate the fourth root of 27 divided by the fourth root of 9, what I could do here is I could write this as the fourth root of 27 over 9. 27 divided by 9 is 3, so this is just the fourth root of 3. Again, similar to exponents, if you take a radical and then you take another radical, you multiply the indices. So, what I mean there is the square, if I do like a square root of a, and then if I was to take a cube root of a after that, I would have that this is the sixth root of a, not the fifth root because you multiply them. Also, we have that cancellation this way does work. So unlike our last example, if I do the square root of 6 squared, that does in fact equal 6. Again though, keep in mind, the square root of negative 6 squared does not equal negative 6 because it's not a real number. Because you'd have to be able to take the square root first. Now, for an even, as we already saw, this happens. However, for odd powers, it's not a problem because an odd multiplication preserves negatives. Namely, if I do the cube root of negative 125, that is indeed just, since negative 125 is the cube root of negative 5 cubed, this is just negative 5. Now let's work an example. Let's go ahead and use our properties to simplify each expression. We have the square root of 8 times the square root of 2 is the same thing as the square root of 8 times 2. That's the square root of 16. 16 is a perfect square, and its answer is 4. Here, the cancellation works perfectly this way, so we can just write 5. Here, however, it doesn't work perfectly, so we need to be a little bit careful. But the good news is that x cubed, that this way, since it's an odd root, we can go ahead and do the cancellation as always. However, here, because it's an even root, we can't. We actually have to write that this is the absolute value of y. So now it's time for you to try an example. Go ahead and use the properties of radicals to simplify each of the following expressions. And go ahead and pause the video, and on the count of 3, I'll reveal the answer. 1, 2, 3. So now you can go through and check your solutions. For more practice in working with radicals, be sure to see pages A23 and A24 of the textbook and work problems 3 and 39 through 42. And in our next video, we'll go ahead and talk about simplifying radical expressions.